In the world of next-gen manufacturing, the line between a total masterpiece and an absolute disaster can be thinner than a human hair. Seriously, we're talking about these tiny, almost invisible flaws in materials that can lead to, well, catastrophic results. So today, we're diving into how AI is becoming the ultimate quality inspector, an inspector that can spot things even the sharpest human eye would just glance right over.
Just think about that for a second. A microscopic crack hiding in a turbine bleed, a tiny weak spot deep inside a composite wing. In high-stakes fields like aerospace, these aren't just little mistakes. They're potential disasters just waiting for the right moment. The pressure for absolute perfection is just immense. So the real question is, how do you even begin to find a problem that you literally can't see?
This quote from a really recent survey just nails it. Material defects aren't some minor headache you can ignore. Nope, they are a fundamental, core challenge that directly threatens how a product works and, way more importantly, public safety. This is exactly why finding them has become one of the most critical jobs in all of modern industry.
So to really get our heads around this revolution, here's how we're going to break it down. First, we'll look at the staggering cost of these tiny flaws. Then, we're going to trace the journey from human eyeballs to smart algorithms. We'll introduce you to the AI quality inspector, see how it plugs into a zero-defect strategy, and then we'll take a peek at what's coming next on manufacturing's new frontier.
Okay, let's start with the stakes, because they are incredibly high. We're calling this the billion-dollar flaw for a reason. The fallout from missing just one of these defects can ripple out, costing companies fortunes, and in the absolute worst-case scenarios, costing lives. This is especially true in industries like aerospace, where precision and safety are everything.
What you're looking at here is a devastating domino effect. It all starts with one tiny part failing, right? But that one failure compromises the performance of the whole system. That can lead to catastrophic safety events, create mountains of wasted material, and even cause a company to violate strict industry regulations. It is a chain reaction, and every single link in that chain represents a massive, massive cost.
For decades, our first line of defense was the human inspector. But as manufacturing got faster and parts got more complex and way more precise, the limits of the human eye became a serious bottleneck. It became clear we needed a totally new way of looking at things. And this comparison really gets to the heart of it. Let's be honest, manual inspection is subjective. What one person flags as a defect, another might completely miss. And people get tired. After hours of staring at parts, mistakes are going to happen. It's slow, and it's just not practical for the massive scale of today's factories. But automated machine vision, it's objective, it's tireless, it's super fast, and you can scale it up as much as you need. It's a complete game changer. So step one in this whole evolution was basically giving the factory a brand new set of eyes. Machine vision systems use these super high-resolution cameras to get an automated, non-contact look at a material's surface with incredible detail. But here's the catch. Just seeing something isn't the same as understanding it. And this is where the real revolution kicks in. It's not enough for a machine to just see a potential flaw. It needs the smarts to understand what it's seeing, to know the difference between, say, a harmless little smudge and a critical, stress-forming crack. We had to give those tireless eyes a brain. And that brain is machine learning. Now, the really crucial thing to get here is that we aren't sitting down and programming a computer with a million different rules for what every possible crack looks like. No way. Instead, we're building a system that can literally learn for itself. It looks at thousands of examples, and over time, it builds its own expertise. It gets better and better automatically, just from experience. This learning all happens inside what's called a neural network. And as you can see here, it's a structure that's actually inspired by the way our own brains are wired. This lets the AI go way beyond just matching simple images. It can automatically pick out the subtle features, the textures, the patterns, the weird relationships between pixels that really define what a defect is. This completely removes the need for a human to do it manually. The whole training process is just fascinating. You basically feed the system a gigantic library of images. On one side, you have thousands of pictures of perfect, flawless material. And on the other, you have images with every kind of defect you can imagine, all carefully labeled by human experts. By crunching through these examples over and over, the AI builds this incredibly sophisticated model of what's right and what's wrong, far beyond what you could ever write down in a simple set of rules. So look, having an AI that can spot defects is a massive leap forward. But it's still just one piece of a much bigger puzzle.
I mean, the ultimate goal isn't just to find defects, it's to eliminate them entirely. And to do that, you need a strategy. This brings us to a super important idea, especially in aerospace, called root cause analysis. The concept is simple, but it's so powerful. When you find a problem, you don't just fix the symptom. You keep asking, why? Why did that happen? And why did that happen? You dig and dig until you find the true underlying reason it happened in the first place. AI gives you that critical starting point for this deep dive investigation.
This whole approach gets formalized in frameworks like Six Sigma's DMAIC. It's a data-driven path to quality. First, you define the problem, like, say, a specific type of microcrack. Then you measure how often it's happening, using the AI to get super precise data. Next, you analyze that data to find the root cause. Is it a machine's temperature, a bad batch of raw materials? Once you know, you improve the process, and then you control it to make sure that problem never ever comes back. The AI is what fuels this entire cycle with high-quality data. All right, so where is all this headed? Well, we're quickly moving beyond just trying to copy what a human inspector does. We are entering an era where our quality control systems can see and understand things in a way that is, frankly, superhuman.
And we've got the receipts to prove it. Just look at this report card. I mean, even early methods like k-means clustering were hitting over 90% accuracy, which is amazing. But the modern deep learning models like the superfast ULOv8 and the really sophisticated vision transformers are pushing that all the way up to 98, even 99% accuracy. We are getting insanely close to perfect automated detection.
So what's the next big hurdle? Composite materials. These things are everywhere, in aerospace, cars, wind turbines. They're amazing, but they're also incredibly complex. Their layered, non-uniform structure means defects can be hidden deep inside and fail in really weird ways. This is where combining AI with advanced imaging like X-rays and thermal cameras is becoming absolutely essential.
And that brings us to a final, pretty mind-bending thought. We're right on the edge of a reality where our AI quality inspectors can spot patterns of failure in data that, to our eyes, just looks like random noise. They're going to see flaws that are literally invisible to us. So the real question becomes, what kind of new designs will this unlock? What new level of safety can we possibly reach when we can finally truly see the unseen?